Okay, welcome back to EE210B. We are going to continue our discussions of stochastic gradient algorithms. In the last two lectures, we established that these algorithms, under certain conditions on the cost function and the gradient noise process, we established that the algorithms are stable. The second order moment and the fourth order moment of the weight error vector converge to bounded regions. In the last lecture, we developed a long-term model, which I will be using today to assess the performance of the algorithms. You will understand better today the convenience of that model. Okay, so just to remind you of what we have done so far and to motivate the discussion that will follow next, let me start by saying that the material in this lecture is also based on Chapter 4. The pages are indicated over there. Okay, so this is our problem formulation. We have a cost function. We assume that the cost function, as usual, is strongly convex, so its Hessian matrix is bounded uniformly from below, but we are also going to assume that it's bounded from above, like you see it in the last equation on this slide. And the problem is we would like to find the unique minimum of this cost function using a stochastic gradient algorithm. That's because, like we explained many times, we don't know exactly the gradient vector of J, but we are going to replace it by an approximation. Okay. So these are the standard conditions. I'm repeating them just for the sake of reference. The cost function is assumed in this presentation to be twice differentiable, strongly convex, which explains the bound from below, and the gradient vector is Lipschitz, which explains the bound on the Hessian from above. Okay, so these are the standard conditions. We can replace all of them by saying simply that the Hessian matrix is uniformly bounded from below and above. Okay, so this is the condition, the standard condition that we have been using so far. And the stochastic gradient algorithm we introduced 2 lectures ago is what you have up here in equation 5. The new weight is the old weight minus a step size times the approximate gradient vector. And because we are using the approximate gradient vector, that ends up introducing gradient noise into the operation of the algorithm, and the gradient noise process is defined by equation 6 on this slide, which is the last equation. And what we showed 2 lectures ago is that under certain conditions on the gradient noise, for example, we introduce certain bounds on the second order moment and the fourth order moment of the gradient noise process. These were bounds on quantities of this type, if you remember. Right? This is the second order moment conditioned on past information. We introduced a bound on it, and we also introduced a bound on the fourth order moment when this 2 was replaced by 4. Right? So under these conditions on the gradient noise process, you can go back to that section and find out exactly what the conditions are. And we explained at that time that these conditions are reasonable. They are satisfied by several problems of interest. Under these conditions, we showed that the stochastic gradient algorithm will be stable in the sense explained on this slide. That, for example, if you take the second statement here, this is saying that the variance of the second order moment of the weight error vector converges to a region of size proportional to mu, of the order of mu. So if this is your solution here, the red circle denotes the location of the solution, and if this distance here is measuring the size of the error vector, right, which is the distance between omega O and where you are, then on average, that square on average stays within a circle whose radius is of the order of mu. So if your mu is very small, that circle will tend to be very small. Of course, these results simply tell you that the algorithms are stable from whether you are looking at second order stability or fourth order stability, that the error vectors remain bounded, but it doesn't tell you exactly what is the size, for example, of the variance of the weight error vector. of the order of mu means it's some multiple of mu, and we would like to know more specifically the exact expression for the mean square error variance on the right-hand side here, because if I know that value, then I will be able to specify more accurately the performance of the algorithm, and with an expression like that, I will be able to compare different algorithms against each other and say which ones deliver better performance. Okay, so this is what we did 2 lectures ago. Okay, now, in the last lecture, I introduced some notation. So I just want to remind you of the notation. This is the covariance of the gradient noise process, right? S is the gradient noise process. It has a covariance matrix. This is the conditional covariance matrix. So conditioned on the past, I call that RS at time I, because this is the gradient noise process at time I, evaluated, of course, at whatever W you are using here. Okay, so this is just the conditional covariance matrix of the noise process. As defined, this is a random quantity, because when you condition on past estimates, right, so these estimates are treated as constants under this expectation, so they remain present here. Okay, so that expression for RSI is actually a function of the weight vector, and therefore it is a random quantity. Okay, so this is the definition of the covariance matrix, and then a particular case of it, if I replace omega by the optimal value, and take the limit of this definition as I goes to infinity. That's another definition we introduced. So we are going to assume that when you evaluate it at the optimal solution, that covariance approaches a constant value, which I call R sub S. And last time I showed you examples. I showed you that in the quadratic case this happens. I showed you, for example, in the logistic regression case, this happens. If you compute the covariance of the gradient noise at omega 0, you will still get gradient noise present in the problem, and the covariance matrix will indeed, under this definition, go to a constant value R sub S, and I told you what this value is. Okay, so these are just 2 definitions that I am reminding you of. The first is the covariance matrix defined broadly, and the second one is when you evaluate it at the optimal solution and let I go to infinity. That's essentially telling you the amount of covariance, noise covariance, that is retained in the limit. Okay, so this is definitions, and I showed you last time how to compute them for at least 2 cases, the mean square error case and logistic regression case. And then another thing I did last time, I introduced 2 additional conditions and I motivated them. And I used these conditions to motivate a long-term model, which I'm going to remind you of very shortly. So first, I assumed, in addition to the conditions we introduced on the Hessian, that it's bounded from below and from above, I introduced the Lipschitz condition on the Hessian matrix. So let's assume that the Hessian matrix of the cost function satisfies the first Lipschitz condition that you see here on the slide. There is some constant, and delta W is the change, that is the size of the step that you take. So this amounts to saying that I'm assuming that the Hessian matrix is smooth enough around the optimal solution. For example, again, we showed last time that for quadratic risks, for logistic regression risks, these conditions are automatically satisfied. For example, in the quadratic case, the Hessian is a constant matrix. So obviously the term on the left will always be 0, and it will satisfy the first condition for some constant kappa. Okay? If you remember, when we studied Lipschitz conditions from the appendices, we introduced a smoothness condition like this to be able to extract more information from the mean value theorems about the behavior of convex functions around the minima. Okay, so this is one condition I motivated last time. The second condition is I'm going to assume that the gradient noise covariance that I just defined also satisfies a similar condition with some power here, and this power can go up to 4 for reasons you'll understand later in the analysis. Again, I showed that for quadratic cost for logistic regression, these bounds are satisfied, and I told you what the values of gamma are. For example, gamma is 1 for logistic regression, if I'm not mistaken, and gamma is 2 for quadratic cost. You can show that the gradient noise covariance satisfies that condition for these values of gamma. Okay? So we assumed these conditions last time, and I illustrated what they mean and what they do. Okay? And then under these conditions, I showed the following. The weight error recursion for your stochastic gradient algorithm is the first equation that you have here on the slide. If you remember, 2 lectures ago, when we were studying the stability of the stochastic gradient algorithm, we derived that weight error recursion. It tells you that the new weight is some coefficient matrix times the previous weight plus a gradient noise process driving the difference recursion. And this matrix H here is related to an integral of the Hessian matrix. It's a stochastic matrix, a random matrix itself, because it depends on the iterate, right? So that's what we derived earlier. Okay, so that's the weight error recursion for the stochastic gradient algorithm, right? If you remember, Wi is Wi minus 1 minus mu, the gradient relative to omega transpose of the cost evaluated at Wi minus 1. What we did, you subtract Wo from both sides. This becomes W tilde, this becomes W tilde, this becomes plus. And then for the gradient of J, we use the mean value theorem to replace it by an integral expression times the W tilde. That's where this integral expression came from, times the W tilde, right? And then, actually, the stochastic gradient algorithm uses the approximate gradients here. So if you replace the approximate gradient by the actual gradient and the noise term, right? So that's where the noise term comes from, right? So this is the evolution of the weight error vector for the standard stochastic gradient algorithm. Now, what I did in the last lecture, if you look at the first equation, we see that the dynamics is controlled by this random matrix H here. It involves a random matrix H here. Okay, that was fine when we were studying the stability properties of the algorithm. That didn't bother us much, and we were able to work around it. For example, we introduced bounds. Because of the bounds on the Hessian, these were transformed into bounds on the norm of H, and so forth. So we were able to handle that. But today, because we are interested in evaluating the performance of the algorithm, I would like to find an expression that tells me what's the size of this second order moment. I would like to know exactly what it is in steady state as I goes to infinity. I would like to find an expression for it. For this kind of analysis, it's difficult to work with the first equation because of the randomness in H. So what I showed last time, I showed that I can replace model 1 by the model below it using the W primes. And what is this model? It's a very similar model. It continues to be driven by the same gradient noise process. Observe that the gradient noise process has the same argument W as in the first equation. It's not W prime. So it's the same gradient noise process is driving both systems. And the difference between the prime system, which I call the long-term model, and the first system is that the random matrix Hi minus 1 is now replaced by the constant matrix H, which is the Hessian. So the dynamics now, the coefficient matrix that's driving the dynamics of this model is constant. And that will facilitate the mean square analysis for this lecture. I'm going to derive, for example, an expression that tells me what's the size of the weight error vector that results from the prime recursion. Right? How far this weight error vector in steady state as I goes to infinity is from omega 0. And then you might say, but then I'm interested in this and you are evaluating this other quantity. And if you remember, that was the theme of the last lecture. In the last lecture, I derived a result, which I will review in the next slide, that tells you exactly how far this quantity is from that. So if I derive an x prime here, I know if I add to it that difference, then I get a good approximation for the x, okay? So just remember, this is the long-term model. So this is what we showed last time, right? So I'm repeating the long-term model here. This is the long-term model. And what I proved last time, okay, so this is a model that holds, and the reason why we call it long-term, like you remember, is because this holds for large enough I. Okay, for large enough I explained that last time, that this model is a good model for the evolution of the stochastic gradient, of the dynamics of the stochastic gradient algorithm, and good in the following way. Okay, so you can see here that the variance of the original system is related to the variance of the long-term model, and the difference is this power of mu. Mu is small and this power is larger than 1, right? So that's the difference. So if I can evaluate this quantity here by using this simpler model, then I can add a term of the order mu to this 3/2, and then I will get that expression, okay? Actually, if you use a weighting matrix here, for example, the Hessian matrix H, if you would like to evaluate the weighted norm as well, the weighted variance, a similar result holds. And you will see why this is also useful. So we proved this, we proved that, and then we also proved the first relation, which tells me that the trajectories of these two models, the original weight error vector and the long-term weight error vector, if you compute the difference between them, the mean square error difference is small, of the order of mu squared. So the trajectories of these models will move together, okay? So this is what we did last time. This was the main results from the last lecture, which now I'm going to use in this lecture. Okay, so last time I explained to you that if I use this model, the trajectories of this model in comparison to the original model satisfy these conditions. So they are close enough to each other. If the step size is very small, they are very close to each other. So if I want to evaluate this, I can instead evaluate this because it's easier to work with this model. It has a constant h driving the dynamics, and then I correct the expression by that, right? So this is the strategy for this lecture. I will focus on the W prime model and then correct it by this term. Okay? So let's move on. Okay? So when I say I'm interested in evaluating the performance of the stochastic gradient algorithm, what do I mean by that? What performance? So there are two performance metrics that I'm going to define: the mean squared deviation and the excess risk. Okay, the excess risk. So what is the definition? I already gave you a hint that we are interested in quantities that involve measures of this kind, and that also involve weighted measures of this kind with the Hessian matrix here. And these two quantities, as you are going to see, are related to the mean squared deviation and the excess risk. Okay, but I'm going to make this definition more precise, okay? So very soon, I'm going to establish relations 83 and 84. So I'm just stating them here to motivate the discussion. I haven't proven these results yet, but this is what I'm going to be showing very soon. I will be showing that, right, in the 2 lectures ago, I showed that this limb sup is of the order capital O of mu, right? Here, what I'm saying, I will be able to characterize the term that depends to first order in mu plus higher order terms in mu. This is a little o here. Okay, so I will be able to show that the limb sup has this form, and I will be able to tell you exactly what this MSD value is, what I'm calling MSD bar, plus higher order terms. In other words, the analysis that's coming will be able to identify exactly the coefficient of the first order term in mu. Okay, so if mu is very small, that is a good approximation for what the limb sup is. Okay, so when you write that this is capital O of mu, right, you can expand it as, let's say, a polynomial expression in mu. You can also do that, okay, because of course for mu very small, the first term in mu dominates. That's why we write it like this, O of mu. But I'm going to show you that actually you can write it as a first term in mu plus some higher order term. And I will also show that the lim inf, remember the lim sup, right, is the bound from above to the limit, the lowest bound from above, and the lim inf is the highest bound from below. I'm going to show that a similar expression holds for lim inf, right, with a minus with a minus sign. Now, why are these expressions useful? Because, you see, if I take the left-hand side and I divide by 1 over mu, 1 over mu. So this mu disappears. And here, because this is little o of mu, so you have higher order powers of mu, you will still have a term that depends on mu after you divide by mu, right? If, for example, if this is mu to the 1 plus epsilon, you will still get mu to the epsilon. Or if this is mu squared, you'll still get mu after you divide by mu. So if you take the limit as mu goes to 0, these terms disappear and you will be left only with the MSD bar, right? So if you do this calculation, right? So here I'm just reminding you of the expressions I wrote. The lim sup is this limit from above, the lim inf is the limit from below, and the analysis that's coming will show you that these limits actually are given by an expression like this. Now, if I do this calculation here, if I divide by mu, okay, and then take the limit as mu goes to 0, both expressions will give me MSD, right? You see, when you study the concept of lim inf and lim sup of a sequence, if the lim sup and the lim inf coincide, then we say that the sequence has a limit. If they coincide, then the sequence is going to your regular definition, regular notion of a limit. And that's what's happening here. You see, as mu goes to 0, the lim sup of this quantity 1 over mu, this normalized sequence, is agreeing with the lim inf of that same normalized sequence. So what this is telling you is that the normalized sequence is going to a limit. Okay? So the normalized sequence, when you normalize by mu, okay, it approaches a limit. Right? As I goes to infinity, this is going to a limit. Okay? And then if I find that limit and unscale, remove the mu again, multiply by mu, I can use that value as a good approximation for what the mean square deviation is, for what they expect for the second order moment of the weight error vector is. Okay? So, the point of this whole discussion is to say, okay, that this quantity here, right, if you compute this quantity, it will have a value. And then if I scale it, that I'm going to take as a definition of the mean square deviation for the algorithm. Okay? This is the definition. Now, you could also use, if you want, the lim inf instead, because they are going to the same value. Okay? So formally, this is the definition of the mean square deviation. Okay? You scale the variance by mu, and then compute these successive limits, and scale by mu again. Okay? Now, often, very often, right, we relax this expression, okay, and we write the following instead. So here is just summarizing what I just said, that because of the expression on top, because these limits approach the same value, then this quantity that you have here approaches the limit, and because of that, I can define this quantity here approaches a well-defined quantity, which I'm calling the MSD. Okay? Now, often we simply write the MSD like this, right? This is if the variance, the second order moment, is converging to a constant value, this definition is perfectly fine, right? But in situations where we cannot assure, right? We cannot ensure that the variance is converging, but we only know that the lim sup, right? We have an idea that the lim sup is bounded, then this is the more formal definition, okay? Very often we use this, we simply write this. Actually, analysis that assume that the second order moment of the weight error vector exists and then evaluates this limit to find expressions for the MSD, you can show, and if you just follow the argument in the notes, you will see that that's the case. The expression that you get from this line of thought and the expression that you get for this line of thought, both of them agree to first order in mu. So to first order in mu, both expressions will give you the same, essentially, will give you the same result. Okay. So here I'm just defining the MSD, right? And this is again saying that this is a less precise but widely used expression for the MSD as well, if you assume that the second order moment exists. Okay? So like I say here, derivations that assume the validity of 87 still lead to the same expression for the MSD to first order in mu. Whether you use the more precise definition or whether you use this approximate definition, the results will be the same to first order in mu. Okay? So that's for the mean square deviation. So the mean square deviation is essentially assessing, telling you what this quantity is. So this is the intuition of the definition. If you look at the value of this quantity in steady state, it's giving you what the first order term, it will give you an expression for it to first order in mu. Okay? It will give you an expression here that is that value to first order in mu. It need not be the exact expression for higher order terms in mu, right? Okay, so the definition I gave you is extracting the first order approximation to the second order moment of the error, and that's good enough. If mu is very small, that's good enough for us, okay? Likewise, I can define another measure. Rather than measuring the difference between the estimate and where you want the mean square error difference, you can measure how far the cost function itself is from the minimum cost. For example, when you study learning algorithms, that's what we are interested in. You are interested in knowing how close the risk gets to the best value it can get to, right? Rather than in knowing how close the hyperplane gets to the optimal hyperplane. Okay, so depending on your problem, you might be more interested in this measure than in the previous measure. Okay, rather than measuring mean square error like this, you would like to know on average how close the cost function is getting to the minimum value. Yes.
Why is it with respect to I minus 1 that time? Or it doesn't matter because
no, this is just a small technicality. You will see from the arguments. Okay, it doesn't really matter. Okay, it doesn't really matter. But this is just to be consistent with something else. Okay. Okay. Fine, so this is on average, and of course, you see, because this is the minimum, this difference is always non-negative. And likewise, if you divide by mu, the same argument will show that if I use this definition will give me an expression for the excess risk to first order in mu. Fine? Okay? Very good. So I have these two definitions, and again, okay, so here the excess risk measures the average fluctuation of the cost around its minimum value, like I said, okay? Now, remember from a few lectures back when we talked about Lipschitz conditions, I explained there that if you have a convex function g, and if the Hessian matrix of that cost function is Lipschitz, right? And I introduced earlier the Lipschitz conditions on the cost function j, right? Then the increment in the cost can be approximated by a second order quadratic expression, by a quadratic expression, right? This is a weighted norm of delta z, weighted by the Hessian. Remember this? And the error depends on the cubic value of delta z, right? Remember? So this was an expression I had before. But this is very similar, you see, this is very similar to, let's say, if I apply this result to the cost function itself, right? What will you get? This delta z becomes the w tilde I minus 1. This is w tilde I minus 1 transpose, right? And in between here, you will have 1/2 the Hessian, right? You see, so what you are getting is, so this is weighted value with the Hessian, right? Okay. So to evaluate the excess risk, right? So under expectation, if you put expectation, then an expectation will appear here, and an expectation will appear here. So whether I want to evaluate the excess risk or the mean square deviation, in either case, I have to evaluate a mean square error weighted with 1/2 h for ER or weighted by the identity for the MSD, right? So that's why in what comes in the slides and the derivations that come later, I will be focusing on evaluating weighted quantities that look like this for some weighting matrix sigma that I am free to choose. So when I want to recover expressions for the MSD, I set sigma equals to I. When I want to recover expressions for the excess risk, I set sigma equals to 1/2 H, where sigma is a non-negative definite matrix that I'm free to choose. So the purpose of recalling this result is to explain to you why is it that when we evaluate the excess risk, we work with weighted norms as well, rather than working with the difference of the cost function. That's because if your cost function is convex, which it is, if its Hessian is Lipschitz, which it is by assumption, then this expression here can be approximated by this weighted norm, and we know exactly the amount of the error. The amount of the error will depend on this, right? The amount of the error depends on W tilde cubed, right? So I make this more precise, I believe, in the next slide. I'll show you that. Let me recall first Jensen's inequality. Okay, remember that if f is a convex function, so f at the expected value of a random variable is upper bounded by the expected value of the function, right? The expected value, you can interpret it as a convex combination, right? Now, if your function is concave, which means the negative of the function is convex, then the inequality is reversed, right? Just remember this. Okay, so if I come back to what I just said, I just showed you that this difference here can be written by this difference, right, like that, plus some error term. So I just want to complete the argument to show you, because of the cubic term that you had there, that translates into an error of this order. So whatever expression I get for this, if I correct it by this much, then I will get the expression for the excess risk. So it's because of this result that whether I'm interested in evaluating the excess risk or the mean square deviation, I can focus on evaluating weighted second order norms. And then when I set sigma to I get MSD expressions. When I set sigma equals to this, I correct it to get ER expressions, right? So where does this come from? Well, we know, right, that the error is related to the cubic, right? And because of the expectation, the error is related to this. So how big is that, or how large is that term? So this is where I apply Jensen's inequality. Here it is. Okay, so so here I replaced by 4 and put out here 3/4, right? I didn't change anything. Okay, sorry, by writing this, right? By writing this, I'm already using Jensen's inequality here, because I'm applying Jensen's inequality to this function. This function is concave over this range. Okay, so if you plot this function over non-negative values of x, it will be a concave function. Okay, it will be a concave function. So because of that, because this function is concave, if you go back to Jensen's inequality, what does it say? It says that f at the expected value of some variable a would be larger than or equal, right, to the expected value of f at a, right? If you go back, here it is. For concave functions, f at the expected value is larger than or equal, right? So here, my f is x to the 3/4, okay? So I have here expected value of a to the 3/4, right, is larger than or equal to the expected value of the function at a. So a at, what do I have now? A at 3/4, right? So if you choose your a to be the fourth norm of W tilde, so look here, what you have on the right is exactly this quantity here, and what you have on the left is exactly that quantity there. So because of Jensen's inequality, the first line holds. But now we know from 2 lectures ago that the fourth order moment, and this was the one reason why we derived the bound on the fourth order moment, that it's bounded by mu squared, and then to the power 3/4 you get 3.5. So we know exactly the size of this. So that's why from now on I'm going to focus on evaluating weighted norms of W tilde in the limit, and then I correct by this expression whenever needed, okay? Very good. So here it is. So this is the definition, the technical definition of the excess risk. Very often we simply write this, right, assuming that this mean converges, right? This is the approximation that we often use, okay, under this assumption. And like I said, the expressions you get from here, expressions you get from there, they will agree to first order in mu, and that this is a good approximation for the excess risk, and we know exactly how much it will differ from that, but by a higher order term of mu, right? So to first order, all these expressions will give me the same value, like I'm claiming that. But to prove it, you can just repeat the arguments that you have in the notes using this definition instead of that, and you will see that that's what you get, okay? Okay, very good. So that's that, okay? This is a summary of the definitions, right? The formal definitions of the MSD, the first equation, right? You divide by mu and then multiply by mu after you take the limits. And that 96 is a valid definition as well, because remember now, 96, because I know that this expression here is this quantity plus a higher order term in mu. When I divide my mu and take the limit, that higher order term will disappear anyway. So this expression and that also are valid expressions, okay? So up to first order in mu, right? If you are interested in the first order terms, which these expressions are giving you, they are giving you the first order term. These expressions are giving you the first order approximations for the MSD and ER. Then you don't need that correction term, okay? Very good. So now we know that all I really need to know is focus on computing quantities like this, the lim sup of quantities like this in the limit under this weight or that weight, or some other weight that you might be interested in. Okay? Very good. So let's now do that. So here I'm just reminding you of what the algorithm is. This is the algorithm that we are studying, the stochastic gradient algorithm. It involves gradient noise, and we defined the gradient noise covariance. This is the steady state component of it, right, at omega 0. We defined it by R sub s, and I showed you last time that in important cases of interest, this RS exists, and we know exactly what it is. Okay, so this is, I'm just reminding you, okay, and that this is the long-term model that I will be using. And why I will be using this model is because I showed, for example, that if I assess its MSD, right, because to assess the MSD, I need to assess limits like this. So if I find expressions for this limit involving W prime, I can correct it to get that limit. And likewise, if I find the limit for W prime here, weighted with H or 1/2 H, it doesn't matter, I can correct it and get that limit, right? Okay. So far, I explained what the long-term model is, why we focus on evaluating its performance, and why these expressions relate to performance expressions, right? Why they give me MSD and ER. I explained why they do that, okay? So now let's evaluate these expressions. Okay? So this is the main theorem that I'm going to prove, okay, in the remainder of this lecture. And then, of course, it has an extension to the complex case. This is the theorem. The MSD and ER, the expressions I defined before, 1 over mu, the limit over mu, the lim sup over I, of 1 over mu, the second order moment of W tilde squared, right? The expressions I defined before, which gives you the first order terms of the first order in mu of the second order moment of W tilde, they are given exactly by these expressions, okay? This is for general cost functions. What are these expressions? The mean square deviation is, you see, it's proportional to mu, so it's linear in mu, first order in mu. Trace, this is the inverse of the Hessian matrix, which you have here. And this is the covariance of the noise, the RS I showed you on the previous slide. For the excess risk, it only depends on the covariance of the noise. So these expressions tell you how the performance. So I'm not telling you, right? I'm not telling you that this enters a region bounded by mu. I'm being much more specific now. I'm telling you that this actually enters a region where the first order term in mu is this, right? Plus higher order terms in mu. So I'm telling you exactly what the first order term in mu is, both for the MSD and for the ER when the weight is 1/2 h. Right? And because we are dealing with small step sizes, then these are very good approximations, expressions, right? Actually, they are exact expressions for the first order terms, and they are very good approximations for what the actual MSD and ER is in steady state. Fine? Number one. And number two, I'm going to show you that the second order moment, with weight or without weight, it is going to converge to this steady state region of size mu and attain these values at this rate. I also have an expression for the convergence rate in terms of the minimum eigenvalue of h. H, remember, is positive definite, okay? So I'm going to derive that. More specifically, actually, what I'm going to do, I'm going to derive these expressions that you see here, 97, 98. Let's look at one of them, and the same remarks hold for the other. Let's look at 97. What I'm going to show is that the limb sup of the second order moment is given by this expression plus a higher order term in mu, 1 plus something positive. And that gamma actually is the minimum of 1/2 and gamma over 2. So it's positive. And remember, this gamma, I assume that the noise covariance is Lipschitz, bounded by some constant times delta omega to the power gamma. Okay, this is this gamma. And I said this gamma is between 0 and 4, right? The important thing to know here is that it's 1 plus something positive. So this is higher order in mu. So now, if you divide by mu, this disappears. Here you still get something that depends on mu. And now take the limit as mu goes to 0. This goes away. You'll get 1/2 of that. Multiplied by mu again, you get this. That's how we get the MSD expression from the previous slide. And similarly for the excess risk, okay? So actually I'm going to show these expressions, and then if you apply the definition to these expressions to extract the first order term, right? How do you extract the first order term that depends linearly on mu? Divide by mu, take the limit, you kill the higher order terms, and then put mu back. That's what these definitions are doing, okay? So I'm going to derive 97 and 98. Actually, I'm going to derive one of them. The other one is just similar to it, okay? Very good. So proof. This is the proof. I'm going to work with the recursion for the long-term model, okay? Sorry, here it's multiplied by I minus mu. So let's do this correctly. Right? So here you have I minus mu h, constant h, w tilde I minus 1 prime, minus mu, and then the gradient noise process, right? This is the long-term model. I'm going to do a change of variable. It doesn't, it's just useful. Introduce the eigendecomposition of H. It's a positive definite symmetric matrix, right? Lambda will have positive eigenvalues, diagonal elements. U is orthogonal. And introduce transformed quantities. So I'm just diagonalizing the coefficient matrix here, right? So W bar is U transpose times W prime. S bar is U transpose times S, right? This is just, so if I multiply, so here, if you replace your H, replace this H, okay, by U lambda U transpose, replace this U, this I, by U transpose, right? Okay, nothing changed so far. Multiply by U transpose from the left here, U transpose from the left, U transpose from the left. So U transpose times S becomes S bar. U transpose times W tilde becomes W bar, right? And then U transpose times this U, right, is I. I take this U transpose out, put it here, because it's common here and there. So this goes back to I minus mu lambda, right? Because this U transpose also cancels this U, right? That's how you get this relation. Okay, so this equation 103 is equivalent to the long-term model, but written in terms of transformed variables, just because now the coefficient matrix becomes diagonal. It's easier to work with, okay? And because the relation between W tilde and W bar is through an orthogonal matrix, of course the Euclidean norms will agree, right? And therefore, if I evaluate the second order moment for W bar, it will agree with the second order moment for W tilde, right? Nothing changes. So let's work with 103. So I'm going to square it now, right? So I'm going to compute a weighted norm relative to some sigma. So next page, here it is. Okay? So let's do it slowly. So I'm going to square this. Okay? And then take the expectation conditioned on the past. Here it is. I squared it, conditioned on the past. Now, square this and condition on the past. Here it is. I squared it and conditioned on the past, right? With weight sigma. Okay? So the notation here, a vector squared sigma, right? This is A transpose sigma A, right? That's the notation. Okay. Now, square this with sigma. So you will get W bar transpose I minus mu lambda times itself times times sigma times I minus mu lambda times W bar again, right? When you square, take the transpose of this times sigma times itself, right? That's what you get. So here it is. It's a weighted norm of W bar again, but with a weighting matrix which is given by sigma prime. Here it is, right? Which I expanded in the last equation. Just expanded it so that you see it has a linear term in mu and a quadratic term in mu. And what about the cross term? You see, the cross term under expectation and condition on the past, this W will be a constant, and the noise, if you remember, its mean value is 0 conditioned on the past. So the cross term disappears, okay? So I just, okay, computed the weighted norm, I get this. Now take expectation again, then that removes the conditioning here, and adds expectation here, right? So, very good. So I get the second expression. Okay, here it is. Okay. Now, all I have to do is evaluate what these quantities are. So I'm going to evaluate the quantities on the right. Okay, this one and that one. Plug back and use that relation to find the limb sup. Remember, I'm trying to find the limb sup of this quantity. Okay. Because here the weighting matrix is different from that, I cannot just take the limb sup, right? So I have to do some more calculations. Okay, so here, let's look at the first term. The first term, I just replace sigma prime by what it is. Remember, sigma prime is sigma minus 2 mu lambda sigma, and then I put the other term, mu squared lambda sigma lambda, separately. Okay? And remember again, this analysis is in steady state because I'm interested in the performance of the algorithms in steady state. In steady state, right, I already know what the size of this will be. Okay, let's look at that. Here, you see this. So this weighted norm, right, is upper bounded, right, because these are, okay, diagonal matrices. I'm free to choose sigma. So I'm going to choose sigma to be a diagonal matrix, okay? So this is a product of 3 diagonal matrices, okay? A product of 3 diagonal matrices, and they are symmetric, of course. This is a diagonal matrix and symmetric. Therefore, right, this norm, right, this is the Rayleigh-Ritz condition that I explained before, right? If you remember, if you have a quantity like this, A transpose times some symmetric matrix A transpose capital A, this is less than or equal rho of A, norm of A squared, right? This is the result, okay, that you can deduce easily from, for example, the Rayleigh-Ritz characterization of eigenvalues, which we talked about before. So that's where you get the first relation, right? And of course, this is the maximum eigenvalue, and this is the sum of the eigenvalues, and this sigma is a diagonal matrix with positive or non-negative entries, so this bound still holds, right? But the important thing is that I removed the weight, replaced it by some number independent of W bar, and this is of the order of mu. I already know this is of the order of mu in steady state, right? So this quantity here is of the order of mu. So this quantity here is of the order of mu, because something times mu. So, and then there is mu squared. So what this says, I can replace this quantity by this, plus a correction term of the order of mu cubed, right? So that's what I did here. Okay? So this, I can replace it by that plus mu cubed. I'm just keeping trace of sigma here, okay? It's not, okay? Fine so far? Okay, so I evaluated this term here. I kept the term, the first two terms, and the last term is of the order of mu cubed. Let's now evaluate the second part here. Okay, the second part. So here it is. This is the second part, okay? So what's that? This is the trace of the covariance, right? If you have a random vector expected value, if A is random, this is the trace of the covariance of A. Let's say if A is a column, A transpose, right? Okay, and if there is a sigma here, okay, if there is a sigma, this is what? This is A transpose sigma A, right? So this is the same. On the left you have a scalar, and you can write this is the same, for example, as the trace of, okay, you can put expected value here of sigma A transpose, right? Trace of AB is the trace of BA, so I can take this A transpose to the other side. Okay, so this is what I wrote here. You see, expected value of A transpose, sigma, and I brought the expected value inside. Nothing changed, right? Why do I do this? And now you will see very soon why I do this. The S bar, by definition, was U transpose S. So let's put back. So the S bar is U transpose S, and this S bar is U transpose S. So replace S bar in terms of S, you will add these U's, right? Okay, the U's come out. Okay? Because remember that S bar is U transpose S. So this here will be replaced by U transpose S. So that gives you this U transpose. And this one will be replaced by S transpose U on this side. And that you can bring it to the front. Okay. Now, why do I do this? Because one of the results we proved in the last lecture, because of the Lipschitz condition because what's this? This is the covariance of the noise, right? This is the covariance of, not in steady state, this is the covariance of the noise. And we impose the Lipschitz condition on it. Because of that Lipschitz condition, we showed last time, that was one of the lemmas last time, that this covariance is close to the steady state value by some difference which we can quantify. We showed this last time. And this is the power of mu, and this gamma prime is given on the next page. It's defined in terms of the gamma, right? There was a gamma which varies between 0 and 4. Okay? So this quantity here is close to RS. That's essentially why we did this calculation. So let's continue. Okay? So this is the gamma prime, minimum between gamma and 2. And remember, this gamma is between 0 and 4. Okay, so this is what we showed last time, okay? We showed last time that this quantity is close to RS by that much. And of course, if I scale it by U sigma transpose, U sigma, U transpose, these are quantities that are independent of mu, okay? So this norm is upper bounded by that norm, this variance minus RS times the norm of this. So this is just some constant. So this difference continues to be of the order of mu to the power gamma prime over 2, right? So this is in terms of the norm of the matrix, okay? But the trace of a matrix, this is a result that you can show. It's a homework problem. You can show, okay, that the magnitude of the trace of a matrix is upper bounded by its norm. Okay, so this is so if the norm is bounded, the trace is bounded. So if this norm is bounded, its trace is also bounded by some constant which you can incorporate into the O, right? So what we have shown so far, okay, so what's the trace of this? Okay, I can bring the U bar back, so then this becomes S bar weighted with sigma. So the trace becomes this weighted norm, right? Okay, and then the trace of this here. Fine? Okay, so what have I shown so far? Remember, we started by wanting to evaluate this quantity. And this is what I showed. I showed that that quantity, right, is close to this quantity by this much. Right? So when you write an expression like this, that the lim sup of A minus B is some value, you are essentially saying that this quantity here is sandwiched between A plus B or A minus B. That's what you are saying, okay? So here it is. The quantity is sandwiched between, because I'm calling this B1, is sandwiched between that value plus B1. Okay, why did I change the notation to B0? So here I called it B1, and here I called it B0. Just some typo. Okay, anyway. The important thing to know is that this is of the order of mu to the gamma prime over 2, okay? So you have that. This quantity that I want is this trace plus some value, or this trace minus that value, where that value is of the order of mu to the power gamma prime over 2, fine? So this argument led to this expression here. Okay, this is the first conclusion. Okay, so remember I had two terms. I evaluated one, I evaluated the other. Let's now put things together, okay? Let's now put things together, okay? Anyway, yeah, so technically this B0 is still of the same order, but actually it is slightly different from this B1. If you want to understand the difference, this is just a small argument. Go back to the argument that I used in the notes to arrive at this recursion. You'll understand, okay? But the important thing is that this B and B1 are of the same order, okay? Anyway, so when I put these things together, look what I have, okay? Here, let me go back. Remember, we started with this energy relation, right? Tells you how the variance is evolving. I replace this by a quantity like this plus mu cubed. And now I can replace this, right? Because I showed that this quantity is something plus order of mu gamma prime over 2, something minus order of mu gamma prime over 2, right? This quantity here. So put that together, you arrive at this. If I use the upper bound, so this quantity is upper bounded by this, plus mu cubed, right? Remember I had a mu cubed? Okay. And if I use the lower bound, right? If I use the lower bound, because that was unequal, I get that this is larger than that, right? Okay. Now I can group, right? Take the limit and group terms. Let's do that next. Okay. So if you take the lim sup of the sum of two sequences, this is upper bounded by the individual lim sups. Okay. This is just a property. And if you take the lim inf of the sum of two sequences, it is lower bounded by the individual sum. By the sum of the individual lim inf, okay? So let's take the lim sup of this. It will be upper bounded by the lim sup of this, right? So there it is, upper bounded by this lim sup plus that quantity. Now we can group this term with that under I going to infinity, right? So this sigma will cancel that sigma. You bring the 2 mu here, right? So if you, and then similarly for the lim inf, okay? So if you group the terms, you get these bounds. Fine so far? Okay, fine, okay. Now, very good. Okay. Now, you have a common mu here. I can eliminate it, right? Eliminate this, and this becomes 2, right? The same thing here. Eliminate this mu, and this becomes 2. Okay, very good. Okay. So here it is. So the lim sup is upper bounded by that, which is the first equation. The lim inf is lower bounded by that, which is the second equation. And of course, the lim inf is, okay. So this is what we proved so far. Now I can get from this the MSD expression. How do I get the MSD expression? First, I can choose sigma to be 1 over 2 lambda, right? I'm free to choose sigma. So let's choose sigma to be 1 over 2 lambda, right? I'm free to choose sigma. Then this becomes I. Oh, sorry, the lambda is a matrix, sorry. Very good. Okay. Sorry, 1 over 2 lambda inverse. Okay, right? Then this matrix product here becomes the identity. Very good. Okay. And what about this? Okay, this becomes 1/2 U lambda inverse U transpose. Remember what H was. H was U lambda U transpose. So this is 1/2 H inverse, right? So here you get 1/2 H inverse RS. Fine? Okay, so let me erase this to save some space. Very good. Okay, so now, how do I get the MSD expression? Okay, so I'm just reminding you that this B0 here, right? The B0 is of the order of mu to the gamma prime, and gamma prime is the min of gamma and 2, and gamma assumes values between 0 and 4. Okay? Okay. So, mu times B0, right? Mu times B0, okay, will be what? So, gamma prime, so this value here, gamma prime over 2, is between 0 and 1, okay? So, mu times that will have, in general, a lower power than mu squared, right? So, it dominates mu squared, okay? Very good. So, just remember, so here I have, you see, I have mu over 2 trace of H inverse RS plus mu times B0, so that would be, right, order of mu to 1 plus gamma prime over 2 plus mu squared. And this is a smaller power of mu than that, okay? Very good. So now if you take the lim sup, right, if you compute, so from here you conclude that this lim sup as mu goes to 0, right, these are all terms, right, that have mu in them. So as mu goes to 0, okay, the lim sup will become this quantity, which is the first quantity, okay, plus this quantity here because it dominates that, okay? It's of that order, okay? It's of that order here. And the same thing for the lim inf, okay? So from these expressions here, from these bounds, okay, from these bounds here, right, as, okay, for mu very small, you will conclude that the lim sup of this is given by this expression, and then I replace B0 by what it is, and then I combined it with mu and mu squared, and you end up having this expression here, okay? Fine? Okay. So now you do the choices that I was talking about there, right? If you choose your sigma to be 1/2 lambda inverse, right? Then this term here becomes mu over 2 trace of H inverse RS. Fine? And then, now, divide by mu. So this mu goes away. You remove 1 from here. Both of them are larger than 1 in exponent. You remove 1, right? So divide by mu. You will continue having a term here that depends on mu. And then when you take the limit as mu goes to 0, this term disappears. Put mu back, then you end up with this expression, right? So you end up finding that the MSD is indeed given by mu over 2 trace of H inverse RS. Okay? Very good. So this we got it from these bounds, right? Okay. And this is, and remember, and this is what I said earlier today, that I'm going to show later that the lim sup and the lim inf, right? So these are the next expressions here, that the lim sup is some mu times some MSD bar plus some higher order term of mu. This is the expression. And the lim inf similarly. Okay? And this gamma over 2, it came from the gamma prime, because the gamma prime is defined in terms of gamma. Okay? So when you combine mu b0 with mu squared, you end up getting the minimum of 1 plus gamma over 2. Okay. So now, I showed what this quantity is. But remember, this quantity, the limb sup of this quantity is this far away from the limb sup of what I want, right? The second order moment of the true stochastic gradient algorithm. So I have to correct, right? I have to add to this, right? So here, a minimum of 2, 1 plus gamma over 2. I have to also add the 3/2. Okay? So you will have mu 3/2, and then you'll have the 2 min of 2, 1 plus gamma over 2. And of course, the power of mu that will dominate, right, is given by the smallest among these values, right? Okay, so that's why, so remember, 3/2, 1 plus gamma over 2. If you go back to the statement of the lemma, that's why I said 1 plus gamma m, and gamma m you see here, so it's 1 plus minimum of 1/2. This is just another way of writing it, okay? This is just another way of writing the minimum of 3/2 and 1 plus gamma over 2, okay? Three halves, 1 plus gamma over 2. Okay, so we proved that. And similarly, for the lim inf, okay, we don't need to worry about it, but just to complete the argument. Okay, and what about the rate of convergence? Okay, what about the rate of convergence? So if you go back to the recursion we had before, I just rewrote it here. Okay, I just rewrote it here. This was mu cubed, so I just write it as a higher order term of mu squared. That's not wrong, okay? I just rewrote it here. Now I want to know at what rate this is approaching that value, okay? So let's call this matrix I minus 2 mu lambda, call it D. It's a diagonal matrix, okay? And call this matrix U transpose RSU, just call it Y, just to keep things simple. So that recursion, right, becomes here D sigma trace of sigma Y, and then trace of sigma times that, right? Okay. Now, this matrix here, when mu is very small, it's a stable matrix, right? It's a stable matrix when mu is very small, and actually we know what rho of D will be in that case. It will be 1 minus 2 mu lambda min of lambda, which is lambda min of H, right? Okay. Therefore, this D is a stable matrix for mu very small, and it converges to 0. Powers of it converge to 0. And so, this sum of D, right, this is like a geometric series, right? This sum is I minus D inverse. If you replace D by what it is, you get this quantity, right? Because I'm going to use this in my arguments, okay? Now, so if you iterate this recursion, okay, let me show it here. If you iterate that recursion, okay, so I think I have this slide. Okay, here I'm just stating properties of D which I'm going to use, okay? I'm stating properties because what I'm going to do, I'm going to iterate this recursion. When I iterate this recursion, powers of D will come up, and a series involving the sum of powers of D will come up, okay? So I'm just showing that the sum of the powers of D is that, and because this sum converges to 1 over 2 mu lambda inverse, when you multiply by O of mu squared, you will get something which is higher order in mu, right? Okay, so given this, so let's iterate. So this is my recursion, okay? This is my recursion, and let's set this sigma successively to the following value. So when I set it equal to I will get D here, right? And then when I set it equal to D, I will get D squared. When I set it equal to D squared, I will get D cubed, okay? So you can write down this equation for successive powers of sigma, and then you add them up. You will be able to find that the value of the variance of the error at time I, you can relate it to the variance at the initial time instant involving a power of d plus this sum plus that sum. Okay? By the way, that was one reason why I kept the trace of sigma here multiplying mu squared. Okay? Because if you embed it into the higher order term, then when you are iterating this recursion here, you will end up with a sum of 1 plus 1 plus 1 plus 1 plus 1. As I goes to infinity, that's become a divergent sequence. So, it masks what's really happening. If I keep it as trace of sigma, and this sigma will be I d squared, and this sum converges, doesn't diverge. Okay, that's why I kept the trace of sigma there. Okay, so now if you look at this recursion, you will see that this converges at a rate that's determined by the spectral radius of d, because you have the power of d there. And the spectral radius of d, I just showed it is 1 minus 2 mu lambda min of h. So that's the convergence rate is determined by this quantity. Okay, and here you can see that this, as I goes to infinity, this is bounded. So then this continues to be a small order of mu squared. And as I goes to infinity, what do you get here? Okay, trace of d to the ny, this will be trace of I plus d squared, etc. y, right? This becomes I minus d inverse y, the trace of that, right? So let's see what is I minus d inverse. Remember that d is 1 over 2 mu lambda, right? Oh, I minus, sorry. I have it here, what I minus d inverse is. 1 over 2 mu lambda inverse, right? So this is here 1 over 2 mu lambda inverse times y. And the trace of, and then times mu squared, right? So mu squared cancels this mu, I get the mu here. So I get that this converges. After convergence, right? This term goes away. This term is higher order power in mu. This term is first order power in mu. It gives me the MSD value. So this is another way for you to get the trace of H inverse RS. Because what is mu over 2 lambda inverse y? Let's do it here. You see, what is trace of lambda inverse y? Right? Here it is. Okay. Trace of lambda inverse y. And this quantity is actually, okay, because remember, H inverse is U lambda inverse U transpose. And Y is, what was the definition of Y? I introduced it. Here, U transpose RSU. U transpose RSU. So if I come here, lambda inverse Y is lambda inverse U transpose RS. This U I can bring it here because for trace I can change the location of the matrix. So the trace of this, you get trace of H inverse I. So this is another way for you to arrive at the same conclusions that I had before. Fine? So I proved the theorem, okay? And then if you choose sigma to be 1/2 H or 1/2 lambda, you get then the expression for the excess risks. So you can do that. It's not that difficult, okay? Very good. So that's the proof of this theorem, which is the main result of this lecture. So now let me show you some examples and then show you the extension to the complex case, okay? Now, when your cost function happens to be quadratic, okay? From the arguments from the last lecture, it's not difficult to see when the cost function is quadratic, the constant Hessian matrix will agree with that stochastic Hessian matrix. They are the same, right? Because the Hessian matrix is a constant. So the long-term model and the actual error recursion are the same, right? They are the same. Which means I don't really need to worry about evaluating the performance using the long-term model. I can use directly the original model because they are the same. So at the end, when I get my performance expression, I don't need to correct it by adding the power of 3/2, like I did in the general case, right? That's how I got at the end that the performance is mu over 2 trace of H inverse RS plus order of mu to the 1 plus gamma m, if you remember, right? And this gamma m involved the minimum of 1/2 and then gamma over 2, something like that. And this came from the 3/2 that I had to add to correct the performance of the long-term model up to the performance of the actual model, right? Here I don't need to do it anymore. So if you don't do that, if we don't need to do that correction, okay, so if you just want to remember where I did this, here, remember I had to correct by adding this correction, right? I don't need to do that anymore, okay? So it becomes the minimum of 2, 1 plus gamma over 2. And for quadratic functions, gamma is 1. This is what we saw last time. For quadratic functions, gamma is 1. So minimum of 2 comma 2, that's 2, right? So for quadratic functions, for quadratic costs, the expressions that I gave for the performance, they are actually, this becomes the power of 2, okay? Not a smaller power of mu, but power of 2, okay? So that's one thing I wanted to say, okay? Becomes power of 2, both for ER and MSD, okay? Very good.
So it's mentioned gamma is 2 for mean square, it doesn't change.
Yeah, gamma is 2, sorry. Gamma is 2, and then gamma over 2 becomes 1 plus 1, yes. Okay. Good. Okay. Let's look at another example. So this is the example I just went through. Let's look at another example, okay, and connect with the results you already know from, for example, LMS adaptation from 210A. For LMS, if you remember, for LMS, I derived this expression 2 lectures ago. This is the expression for the gradient noise. Here it is. And then if you evaluate it at omega 0, right, when omega I minus 1 is omega 0, this becomes 0, right? So at omega 0, you get only minus 2 U transpose V. So RS, which is the covariance of this at omega 0, right, you will get 4 sigma V squared RU. You see, that's how you get it, okay? This is how you show that for in the quadratic case, you have an RS and it's given by this quantity, right? Okay, so now, what is H in the quadratic case? So this is the case where I'm solving a mean square error estimation problem, right? D, expected value of D minus UW squared, right? What is R? What is the Hessian matrix in this case? I'm talking about the real case, 2RU, right? This is the Hessian matrix. And what is RS, the covariance of the noise in this case? Here it is, 4 sigma V squared RU, right? And what is the MSD now? According to the theorem, mu over 2 trace of H inverse, so 1/2 RU inverse, right, times RS, 4 sigma V squared RU. So what do you get? Mu over 2, this RU inverse cancels that RU, 4 over 2, that's 2, so remove this 2, right? And you get trace of M sigma V squared. This is exactly the expression we derived in 210A for LMS. The only difference, there was a mu over 2 there. It's just because here when we write the update equation for the algorithm, we are using 2 mu instead of mu, that's all. But this is exactly the expression. So the trace of H inverse RS, this is an extension of what we did for the quadratic case to general cost functions, right? So now we have a general result that allows you to assess the performance of general algorithms, right? So here it is. And then if you apply the same thing for the excess risk, you get the expression we had before for the excess mean square error. Because that's what it is called in the context of adaptive algorithms. The excess risk is called excess mean square error. Okay? By the way, this is just a simulation here. Okay? Running over data generated by a linear regression model like this, of size 10 taps. This is the variance of the noise, the covariance of U, and this is the step size I used. I ran many experiments, and in each experiment I generated this curve, the error curve, in each experiment, and then I averaged the curve over 2,000 experiments in this simulation, and you plot it. That's why you see a very clean curve. That's because it's averaged over many experiments. But what I want to show is, this is the expression the theory tells you that the steady state MSD value is mu sigma v squared m. Here it is, and you can see that the curve indeed tends to that value, right? For small mu. The result is for small mu, of course. The smaller your mu is, the better the match between theory and simulations, okay? Okay, let's go. This is for logistic regression, okay? For logistic regression, again, we showed that the gradient noise at omega 0 is given by this expression. So the red text that you see here is a typo in the notes. So whenever you see there are a few places where I have red text, it means this is missing in the notes, or there is a typo in the notes. Just add it there. In this particular case, it's missing. Okay, so here it is. Okay, so this is the gradient noise. Okay, if you download the PDF file from my website, you will get it like this already. Okay, so this is the gradient noise, and then we can evaluate its covariance matrix. Again, this term is missing. There it is. And therefore, the excess risk in this case, right, from the theorem, it depends on the trace of RS, which, by the way, since this is less than 1, it's less than the trace of RH, okay, in this example. So if you can find out what RS is, then you can find the excess risk. Either way, it will be of the order of mu, okay? This is for logistic regression. And this is, I have a simulation here for a filter of size 50, regularization parameter 10, step size, and I'm averaging over 100 experiments in this case. Okay. So this is just to show you that the excess risk expression is also performing well and matching well with theory. Okay, that's all. Okay. More generally, not just logistic regression, for any other learning algorithm you take where you would like to minimize a particular cost, and you use a stochastic gradient algorithm by using the gradient of the loss function, right? When you do that, you get a gradient noise, which is the difference between what you want to use, the true gradient, and the approximate gradient. Then RS, by the way, which is the covariance of this at omega 0, then this term disappears at omega 0. So it's just actually the covariance of the approximate gradient, right? And then the performance will be given by the statement of the theorem, okay? So the important thing to note is that you have now a result that tells you exactly what performance to expect in steady state for small mu, right? Very good. So what remains now is to extend the result to the complex case, right? An important detail will come up, and that's why I like to also show you what happens in the complex domain. In most of the results so far, there wasn't much difference except for a type factor H, which is 2 in the complex case, that appears in the expression. In the performance expression, something more will happen, okay? And you will understand why. First of all, remember that in the complex case, I assume that the Hessian matrix is again bounded. Right? H is the type variable, H is 2 for complex, H is 1 for real, so that's why I write it like this. Okay, so that even if you look at the statement of the result in the complex case, if you set H equals to 1, you can recover the results for the real case, okay? So this is the standard assumption in the complex case, okay? This is the type variable, okay? This is the stochastic gradient algorithm in the complex case, so the gradient relative to omega star. This introduces gradient noise, right? Similar to what we have done so far, okay? Now, what you are going to see that the performance expressions will depend on the covariance matrix of an extended noise vector. Remember, in the real case, the performance, for example, for the MSD was mu over 2 trace of H inverse RS. And what was this RS? This RS was the covariance of the noise, right, itself at omega 0, right? The limit of this as I goes to infinity, right? Okay. Now, in the complex case, the argument will show that this RS, because remember, in the complex case, the Hessian matrix is 2m by 2m, right? It's enlarged. So the RS will be enlarged. It needs to be enlarged. The way it will be enlarged is as follows, okay? We define an extended gradient noise vector. What is the, right, just like we did before, for example, omega, you extend it like this, omega star transpose. You do the same thing, S star transpose. You extend it, okay? So the top part is a column, the bottom part is also a column, okay? Extend the vector like this. So this is now 2m by 1, and define its covariance just like before. So I use the E, the superscript. Whenever you see the superscript E in my notation, these are extended variables. That's all. Extended in what way? In this way. So this is the covariance of the extended variable. That's it. This is noise, okay? Now, so the argument will show you why these appear, okay? For now, I'm just defining them, okay? Now, because this SE is the extension in this manner, when you evaluate S times S star down here, right, you will get a 2m by 2m matrix which contains these entries, right? Okay, so you see the 1-1 block of it is the usual covariance of S. The 2-2 block of it is the transpose of it. And then the off-diagonal elements, this is the SS transpose. This is not a real covariance matrix in the complex case, right? And its conjugate. So you see that now two quantities appear. The standard covariance matrix, right? And this other term which is not a covariance matrix. It is symmetric. This is Hermitian and a covariance, and therefore non-negative definite, this first one. The second one, all you can say about it, it is symmetric, but it appears. So now the performance will depend on these two quantities, not just on the covariance of S, okay? Of course, in the real case, both of these quantities are the same. In the real case, only one of them appears, but in the complex case, they are different, okay? So, I'm going to define RS. I defined it before. RS, I defined it as the covariance of S in the limit at omega 0, right? I will continue to use this notation, RS for the covariance, okay? And RQ for the transpose in the limit, okay? So I'm going to assume that these limits exist. So even in the real case, RS was this limit, but I'm still going to use RS. In the real case, I'm going to use RS to denote the actual, in the real and in the complex case, I'm going to use RS to denote the actual covariance, whether it is defined with T or star, first line here, RS is the actual covariance. RQ is the supporting second order moment that you have here, okay? Okay. So here it is, okay? So my notation, whenever you see RS, it is actual covariance, which means in the real case it is like this, in the complex case it is like this. This particular quantity in the complex case I denote it by RQ, because it's not a covariance, okay? So this is my notation. Very good. I haven't explained yet why these quantities appear, but you will understand it very soon. Okay, and remember that in the real case, I assume that the noise covariance satisfies the Lipschitz condition with a gamma between 0 and 4. Okay. Now we need to assume that the extended, right? The extended covariance satisfies that condition, so that the arguments would extend. Okay. So now this is the statement, and in the proof of the statement, you will see why the this extended covariance matrix here appears, okay? So let's look at the statement. Very similar to what you had before. You have here the lim sup for the second order moment of the error and the lim sup for the mean deviation of the cost. The correction term continues to be the same, 1 plus something positive, so it's a higher order power of mu, right? That's the important thing, that this gamma m is positive. Right? The actual expression, you have it, but the important thing to know is that this is a higher, that's why I write it like this, 1 plus something, okay? That this is higher order term, this is first order term. Here you still have H inverse, it's now 2m by 2m, But here, you will have this extended covariance, right? RS, RS transpose, RQ, RQ star. Okay? Now, the expression for the excess risk continues to involve only RS. Okay? RQ is not, doesn't interfere. Doesn't interfere, okay? Actually, why it doesn't interfere? Because the expression that you would get would be, okay, let me show you. Before, it used to be mu over 4 trace of RS. But this is now the covariance matrix that will appear here. The trace will be 2 times the trace of RS. So that's why you can write it as trace of RS alone, and the 4 becomes 2. That's why, okay? Very good. Again, if your H inverse happens to be block diagonal, then the performance will only depend on RS. But when your Hessian is not block diagonal, then you see that the other moment comes in, right? This is something that I explained earlier when I was talking about Hessian matrices in the early lecture, that if the Hessian matrix is not block diagonal, that influences the dynamics in a certain way, okay? And you see it here, okay? So let's continue. Maybe we need to turn this off. Anyway, so let's continue. So I need to prove this result now, okay? And then, of course, you can find out what the MSD expression is and the ER is. Divide by mu, take the limit as mu goes to 0, and then put the mu back. You see, these are the expressions in the complex case, and you can see the difference now. RQ appears. The convergence rate will continue to be 1 minus 2 mu lambda min. So let's show you now from the argument, you'll understand why this comes up, okay? Why it comes up. Okay? This is the argument. Okay? The argument, first let's write down the recursion in the real domain, right? In the real domain. So if you write down the recursion, right? Take your W, introduce take your W, introduce its real part and imaginary part, and then V is the extended vector which contains the real and imaginary part of W, right? And you write down the recursion here, okay? Where mu prime is mu over 2. We showed in an earlier lecture that the complex domain stochastic gradient algorithm is equivalent to this real domain stochastic gradient algorithm. Okay? Very good. Okay. Now, I already know how to write down the performance of this algorithm, right? If you write down an algorithm in the real domain, I know what its performance is. Its performance will be in terms of the trace H inverse RS, where H is the covariance, right? The covariance of J, is the Hessian of J of V relative to V. And RS is the covariance of the gradient noise in the V domain, right? So the gradient noise in the V domain, I'm denoting it by T. Okay? So this is the Hessian noise, this is the gradient noise in the V domain. So what I need to find, I need to find what is the Hessian, right, in the V domain. That will play the role of H. And I need to find what is the covariance of this gradient noise, let's say if I call it RT, right? And then trace of this H inverse times this RT times mu prime over 2 will be the performance of this, which I then translate into the complex domain, right? Okay. Now, I know how the Hessian in the V domain relates to the Hessian in the Z domain. That we know, we already know. And I also know how the gradient noise in the real domain relates to the gradient noise in the Z domain. We know it in the complex domain. We know it from 2 lectures ago. So let me remind you. We showed 2 lectures ago when we were studying the stability of stochastic gradient algorithms that when you write down the stochastic gradient algorithm in the real domain, the gradient noise in that domain is given by this expression. Okay, you can relate it to the gradient noise in the complex domain by this expression. Okay, remember, so S is the gradient noise in the complex domain. It has real part, okay, time I, real part, and it has an imaginary part, okay? real part, imaginary part. We showed 2 lectures ago that the gradient noise in the real domain is given by this expression. Here too, real part, imaginary part of S. Okay? Yeah, I have it written here. I didn't need to write it, okay? Okay, so let's now find out then what is the R sub t, meaning what is the limit, right, as I goes to infinity of the expected value of Ti at the V0, right? Ti transpose at V0, right? Because this is what will appear in the expression, right? This RT times the covariance times the Hessian in the V domain. Okay. So first of all, in the Hessian in the V domain, we know how it is related to the original Hessian, right? This is something we saw many times before. You just multiply by this matrix D, D star. Remember that D had I minus I, Ji minus Ji, something like this, right? Okay. And that D, D star is equal to 2 times I. Very good. And this relation, okay, tells you because D, D star is 2I, right? So the inverse of D star, or the inverse of D is D star, 1/2, okay? So this tells you that this matrix and 1/2 of that matrix are similar to each other, right? Similar to each other. So they have the same eigenvalues. That's where this relation comes from, that the minimum eigenvalue of the Hessian in the real domain is 2 times the minimum eigenvalue of the Hessian. Okay, that's because this is useful because once I write what the convergence rate is in the real domain, I replace lambda min by this, I will get it transformed into the complex domain. Now let's find this limit here, right? Well, to find that limit, this is what I'm going to do, this calculation, okay? Let's take RT, right? Because remember, what is this T? This T is S real, S imaginary, right? And then I'm going to multiply it by S real transpose, S imaginary transpose, right? Okay. So this is what's sitting here. And then multiply it by D from the left, by D star from the right. If you do this algebra, this is simple algebra, you will find out that this quantity on the left evaluates to what you have up there. And you see what you have up there is apart from a 4 here, okay? When you do the calculations, this 4 will come up. You see what you get up there is exactly the extended covariance matrix. So the covariance RT up to the DD star, which we are going to get rid of it very soon, the covariance of the gradient noise in the real domain is related to this extended matrix, okay? So now, given these results, let's look at this, okay? So the previous lemma, let's apply the previous lemma to the real case, okay? So the second order moment in the real case, that's the V domain, is equal to what? Mu over 2. Mu is the mu that you are using in the real domain, so it's mu prime. Trace times the Hessian in the real domain, right? The Hessian in the real domain times the noise covariance in the real domain. And then here you will have something of the order of the step size you are using. And then remember, it was 1 plus gamma m, right? 1 plus gamma m, which I'm just calling m just to simplify notation, okay? Some power m here, which is larger than 1. Of course, mu prime to the m is simply mu to the m, okay? So now, I know what the Hessian of V is in the real domain related to, here it is, I know what this is. So bring D here, D inverse, you remove this D, D star inverse, you remove that D, right? So you can't replace, okay? So you just use this relation to replace, sorry, I have the Hessian of J relative to V is D star HD. I don't need to do that. If I need the inverse, so just invert this, right? So you get D inverse, H inverse, D minus star. That's all, right? Okay, very good. Now, because this is trace, I can take this D inverse to the other side. Here it is. Okay? But now I know what's the inverse of D. It's 1/2 D star. I know what's the inverse of D star. It's 1/2 D, right? Very good. And here, notice that I already replaced mu prime by mu over 2, okay? But now 1/2 and 1/2, that's 1/4, right? 1/4. And dRT d star is 4 times that. So the 1/4 cancels the 4, and you get this result here, which is exactly what the theorem says, right? So you see now where this quantity comes from, right? So this is, and then you can do a similar calculation for the excess risk, okay? I have it here. I don't need to go through it. It's a similar calculation, right? Trace of RT, and then you can add DD inverse, and then replace DD inverse by D star, right? Then it is the trace of this, and then the traces are the same, right? And what about the convergence rate? Well, the convergence rate is 1 minus 2. The step size you are using, the minimum eigenvalue of the Hessian in the real domain. Well, the step size you are using is mu/2, and the minimum eigenvalue is 2 lambda min of H, so you continue to have 1 minus 2 mu lambda min, right? The 2's cancel each other. Okay, so convergence rate continues to, but remember, this H is twice as large, right? Okay, very good. So we prove the theorem. Just to conclude, let me show you some quick examples. Let's take the case of complex mean square error estimation. So now I want to solve a problem like this. Minimize expected value of t minus uw squared. Okay, so what is the Hessian matrix in this case? Here it is, right? Block diagonal, R transpose. Okay. And what is RS in this case? It's easy. You just go back. Sigma V squared RU. And this is that extended covariance matrix. Extended covariance matrix will have RS, sigma V squared RU, RS transpose. Something here, I don't even know what they are. I don't care what they are. Why? Because H is block diagonal. Because H is block diagonal, when you multiply H inverse by this, it's going to extract, right, the block diagonal, okay? So when you do that calculation, this is the performance expression in the complex case, okay? And by the way, in the real case, we did not have the 2. In the complex case, you have the 2. So if I just replace this by H, I capture both situations, right? Okay. And this is one final remark to say, okay, that this matrix, which I defined, the extended matrix, which is the covariance of the, this matrix here, which appeared in the performance expression, it's simply the covariance matrix. It is the actual covariance of the extended vector, right? You just extend the vector, compute its covariance, then you will find these 4 entries here, right? The 4 entries that you have there. Okay? So I can write the expression in terms of the covariance of the extended noise. Okay? So that's essentially what I wanted to discuss with you today. Okay, so what we did today, I evaluated how close W tilde gets to WO, right? I evaluated how small this quantity gets in steady state, and I found a first order expression for it. I found exactly what the first order term is, right? Both for the second order moment of the error and also for the average fluctuation around the minimum value. I also found what the first order term is plus some higher order term, right? And I gave you exact expressions for these terms. That's what we did today, both for the real case and the complex case. Fine? Any questions? No questions? Okay, so I'm going to conclude here today. Thank you.